Great. All right. So thank you so much for the invitation and also for such a gracious introduction, Dylan. It's a real pleasure to be here speaking with you all today. Okay, there we go. So as was mentioned, my lab is located inside of the Shirley Ryan Ability Lab, which is a rehabilitation hospital in downtown Chicago. We were called the Rehabilitation Institute of Chicago until about 5 years ago. And at the Shirley Ryan Ability Lab, we focus on addressing motor impairments that remain as a result of injury or disease. And what the space that I work within this field of rehabilitation is functionally assistive machines. So these are machines that are used perhaps after you've left the hospital. Maybe you're still in physical therapy, maybe not, but the whole idea behind assistive machines is that at some point your rehabilitation has plateaued, or we know that there's going to be a gap in function that remains. And these functionally assistive machines help fill that gap in function. Now, across the field, the common challenge with these machines is in capturing control signals from the human body in order to operate them. So perhaps the most poignant example is upper limb prostheses, where typically they are EMG controlled. So an array of electrodes are put on the muscle. Ideally, you want to use muscle on the residual limb because then you can use the same neural pathways in order to control the robotic limb that you would use to control your intact human limb. But this paradox exists where, or this conundrum exists where actually the higher level of amputation, the fewer residual muscles that remain to capture these control signals from. And so the dimensionality of your control interface is going to be lower than the dimensionality of the device that you are trying to control. Even if, as we look at powered wheelchairs, which are actually only a two-dimensional control problem, you're controlling speed and heading. If you look at the image on the right, this is the different interfaces that are available at different levels of spinal cord injury. So you can see for low levels of spinal cord injury, function of the arms and hands remains. So it's okay it's possible to use to operate joysticks with the hand, but as the level of injury rises up the spine, the level of motor impairment increases as well. And it might be that only a head array is able to be operated, which is operated through taps in the head, or a sip and puff, which is operated through respiration. So here's an example of what this looks like. This was a video we took in my lab a number of years ago. This is the same participant operating our robotic wheelchair, but there's no robotics autonomy turned on. So this is just him teleoperating the chair. On the left, he's using a joystick, and on the right, he's using a head array. And what you'll probably notice is that even with using the joystick, which is this proportional control interface, so it means as we deflect the joystick farther, you go faster. So the amount of control response scales proportionally with the amount of control input from the interface. So even though it's a proportional control interface, and you'll see he's also using a T-bar because he can't grip the actual joystick, so he's using a T-bar. Even with an interface that fully covers the two dimensions of the control space and offers a proportional control signal, it's still a really difficult task. And it's even more difficult if you're now limited to the head array, which is just issuing one control dimension at a time. Maybe you can kind of tap two pads at the same time so you get a two-dimensional control signal, but not all the time. And it's just like turning a switch on and off. So it's not a proportional control signal. And so even with the richer interface that fully covers the control space, this is still a hard task. I think that wheelchairs that meet ADA, or that doorways that meet ADA clearance, so ADA width clearance, I think that there's still only about 10 centimeters of clearance in addition to the wheelchair. So it's not a lot of space. And there's a lot of spatially constrained tasks like this that wheelchairs operators need to navigate all the time. As we consider using these interfaces to control more complex machines, so higher dimensional control than just two dimensions, this becomes all the more challenging. So in this lower image, we see the Canova Jaco arm. So this is an arm that was designed to be mounted to a powered wheelchair. It's usually 6 dimensions in its assistive form. For its research form, you can get it in 7-dimension control as well. You can see the inset here. He's actually using his foot to operate this joystick. And so you have this paradox where actually the more likely you are to need assistance from a robotic arm, you're more likely to need that assistance if you are unable to use your own arms and hands. And yet, if you're unable to use your own arms and hands, you're probably going to be limited to these more restricted interfaces that are operated, that only cover perhaps 1 or 2 control dimensions, and that are not proportional. even if you had full use of your arms and hands, I mean, we don't have good 60 interfaces for control, even to teleoperate robots, even within research, even within people with people without any motor impairments. So this is a real challenge within the field. And of course, what happens with robotic arms is that you end up using modal control if you're going to do direct teleoperation, where you have to partition the control space so that you're only covering a subset at a time. So you're maybe controlling an XY, and you have to press a button, you switch control modes, and then you maybe are able to control in rotation, press a button, you can maybe control in the third dimension of rotation like that. Here's an example of what that looks like. So he's operating a 2-axis joystick. Right now you'll see he's using a pen to push a button. So he doesn't have the finger function to actually push the button. So he has a utility cuff with a pen in it, using that to push the to switch control modes. He starts to operate the arm. He realizes he's not in the control mode that he thought he was in, and so he has to go back, which is another challenge with modal control, is remembering where all the controls are, how many button presses it takes to get to the mode that you want to be in. And so he is able to teleoperate the arm, but you can see it's quite a challenge. And this is actually still at least using a proportional control interface, and it's covering 2 dimensions at a time. Okay, so to sort of summarize, what are some of the challenges of assistive machine operation? So operating these machines that were designed to be operated by humans. So first is, of course, the human impairment, that it's masking and filtering the information that the human is trying to get over to operate the machine. We also have limitations of the control interfaces that are accessible to people with motor impairments. And the 2 most common limitations are their dimensionality and their continuity, or their proportionality. And then the third is machine complexity, and this catch-22 of a more severe motor impairment probably requiring more complex assistance, and usually that more complex assistance requires more complex, higher dimensional control signals from that human in order to operate them, the assistive machine. So of course, a solution to this is to add robotics autonomy to these machines. So of course, if you add external sensors, some computing and AI, some intelligence to reason over this information, you can turn the assistive machine into an assistive robot. Oh, sorry. Okay. So taking a step back on where we see robotics autonomy show up within the broader scheme of rehabilitation robots. So within the field of rehabilitation robotics, I tend to think of things in 2 categories. So the first category are robots that are used to rehabilitate the human body. The most common of these, perhaps the most famous of these, is the Locomat, which is the first sort of assistive lower limb walking robot that was used clinically. The other big category is robots that are used, robotic or assistive machines that are used to replace lost function. And within these, the two big categories that are important from the standpoint of autonomy is whether or not they are worn on the body. And the reason why this is important is that when you add on robotics autonomy, you typically add on additional sensors and additional computation in order to reason about that. And so whether or not that is all, for example, encapsulated within a prosthetic limb, and it's all hanging off of someone's body where you're already struggling to get a good fit between the residual limb and the socket of the robotic limb, whether or not all of that weight and computation is actually needing to be supported by the human, or it's supported by the machine itself. For example, adding on a computer on the back of a wheelchair, pulling power from the wheelchair's batteries, not a big deal. And so as a result, we really only see autonomy in devices that are not worn on the human body. There's starting to be some change in that in prosthetic limbs and exoskeletons, but by and large, the majority of autonomous robotics work within the field of rehabilitation robotics is happening on robots that are not worn on the body and that are used to replace lost function. Okay. So I presented this schematic earlier. Now here, really the devil is in the details on adding this intelligence to the machine. And the reason is because if the autonomy steps in at the wrong time or with the wrong control signal, it takes away from the human's autonomy. It's actually worse than providing no assistance at all. So getting this right is really critical. And it's more than just getting the autonomy to not make mistakes, to always choose the correct control signal. It's about how you properly keep the human in the control loop as well. So if we're now looking at assistive partial autonomy, so what's going to be important? So the first is judicial control sharing. So the control sharing that steps in at the right time and steps in with the right signal. And this is just on the prior slide as well. We'll just reiterate that. Okay, so the first study that I wanted to present to you was something we did a couple of years ago with our robotic arm. This is an exploratory study with 4 spinal cord injury subjects and 13 uninjured subjects. And what we were looking at was this control arbitration function. So this is used a lot within the field of assisted or of shared control robotics. And the idea is that this y-axis alpha is dictating how much control lies with the human versus the autonomy. And then things are just being, their 2 control signals are just being linearly blended according to this piecewise function. What you can see is that this piecewise function actually is parameterizable according to these 3 parameters that are basically dictating at what point does the autonomy step in. Once it steps in, how aggressively does it increase its assistance? And then once it's at its maximal level of assistance, how much is that? Is that 100% autonomy, or is that 50% autonomy? Well, that's what these 3 parameters can map to. So the exploratory study that we did in this work was allowing people to customize this function themselves. And we did it in sort of a soft way where they just could provide us with verbal indicators that would maybe say, I didn't want the robot to step in as quickly or as fast. And so we would reduce the slope, or I wanted help sooner. And so we would move theta 1 over toward closer to the origin. And here's a video of what that assistance looked like. You already saw the video on the top. What you can see on the video on the bottom is that people are providing, the control is happening in all 6 dimensions simultaneously. So we're rotating and translating at the same time because the autonomy has stepped in. And that in the study, the inference is trying to pick which of these 2 goals the human is going towards. And that's actually the confidence in the goal prediction is actually what's on the x-axis of that function that I just showed you. So you're not going to provide a lot of assistance until you're very confident that you know which goal the human is going for. I'm just going to share a couple of results from this study. So one interesting result was that the differences between spinal cord injured subjects and uninjured subjects diminished with assistance, but it was actually eliminated with customization. So what each of these different pairings, and when I say pairing, I mean the black and red groups of data. What you see all the way on the left is teleoperation. So this is no assistance. And then we had 2 functions of this linear blending function that we had set ourselves that were sort of a minimal amount of assistance and a maximal amount of assistance. And then all customizations happened within the bounds of those min and max functions. So if you had asked me beforehand, which of these paradigms would have made the performance of the spinal cord injured and uninjured subjects the most similar, I would have said maximal assistance, because that's where the autonomy was playing the greatest role. And of course, the autonomy signal was what was the same between all of them. But that wasn't the case. We still had a difference. It was less significant, but it was still significant, but it still was significant. We had a difference between the 2 groups when we were using maximal assistance, but we no longer had a difference when we were using the user customized paradigms. And so this is suggesting that the people were intuiting something about how they were interacting with the system, and it was causing them to have better performance. They were interacting better with the autonomy, perhaps. There also was a suggestion that user-directed optimization was considering something more than standard cost functions. So 20% of customizations actually had greater completion times, and 40% actually had more mode switches. So this could be sort of akin to effort minimization. So this is again suggesting that something else is going on here, and we aren't quite sure what. Okay, another topic of judicious control is actually which control blending paradigm you use, which control sharing paradigm. So here's an example of 4 paradigms that show up in the robotic wheelchair literature quite a bit. So the first is a blending paradigm, which is similar to what we saw before. Here we have blended with like an immediate goal or with a perception goal, which is sort of a doorway in the top. So here the green outline is the footprint of the robot. We have the user's command in red. We have the autonomy command in blue, and then we have what gets executed in purple. So it could be blended, could be filtered where the autonomy or the human command is capped to never exceed the autonomy's commands. Or we could have something that's a little bit more aggressive, where once we're really close to, or once we're getting close to the perceived goal, we just switch to 100% autonomous control and then switch back to human control after. So we implemented each of these on our robotic wheelchair and ran a study, because what we had seen within the literature was that while there was a lot of comparisons between no autonomy and autonomy, or partial autonomy and full autonomy, we didn't see side-by-side comparisons of the different ways that you can implement partial autonomy. And so what you might notice from watching these videos is that they don't look that dissimilar from each other. And that's what we saw in the data as well. None of them was more successful in terms of, or was statistically different from another one in terms of the kind of measures that we typically use in robotics, like number of collisions, task completion time, things like that. What we did, however, see was a difference in user preference. So here is the two different interfaces that we used in the study. So we used a joystick and a head array, and each of these color bars represents a different control paradigm. And what we saw was that every single paradigm was selected at least once as most preferred, and every single paradigm was selected at least once as least preferred. I should say that we allowed for ties, so we didn't restrict people to having one that they preferred the most or preferred the least. And we certainly can see some trends, like some are certainly preferred more than others, but it was not uniform across the board that we could have eliminated any of these because it was what nobody wanted. And so all this is really telling us is that we should be presenting people with options. What we also saw was that this was a multi-session study. And so we had, in one session, they would operate a joystick, in the other, they would operate a head array. Some of the spinal cord injured participants needed to have those sessions split in half because of their sitting tolerance, which is why you see this range of 2 to 4 sessions. All of the uninjured participants, it was 2 sessions. But we saw 50% of the time people switch in preference. So their most preferred paradigm switched when they switched the interface that they were using. One thing that I do want to draw your attention to is this 2 to 4 sessions. So this is not a lot of sessions, but it is the case that actually we normally only are evaluating within the field 1 session typically when we bring people into the lab to study. And this is my lab included. I'm also guilty of this. So I want to bring back our list here, our challenges for assistive autonomy, and I want to add on longitudinal and real world evaluations. Now, obviously, there are very practical reasons for why these rarely happen. They're a lot harder to execute, certainly out in the real world, but even bringing back people for multiple sessions, it's a lot more overhead. But what concerns me, and the reason why I think it's very important, is that when we are trying to do things like assess people's preference and assess people's performance, if we are always evaluating their novel interaction with a device and their novel interaction with the control paradigm, I think it calls into question how much we're actually learning. And so I think as a field, if we can move towards multi-session studies being more the standard, it'll serve us well in the long term. Okay, so we just talked about judicious control sharing. The next topic I want to talk about is masked and filtered information. So we talked before about why this might be happening, that the person's motor impairment masks the information that they'd like to transmit to the machine, and also these limited interfaces that are accessible to them. And what's happening is that basically both of these things, their impairment and their interface, is masking their true intent, potentially. Related to this, and I'm not going to get into this topic any further, but I think that an interesting question for us to be considering within this domain is whether or not the autonomy can trust the human. We think a lot about the inverse, whether humans trust robots and humans trust autonomy. But when the role of the autonomy specifically is to fill a gap in human function, so sort of by definition, the human maybe can't issue the control signal that's needed at that moment in time, I think it's worthwhile for us to consider whether or not the autonomy can trust the control information that's coming from the human. And we've done a bit of work in this area, so I'll just pop these citations up here, but I'm not going to talk about this any further in this talk. All right, so there's some work that we've done in my lab about intent disambiguation. So this is related to intent inference, of course, when you're trying to infer which goal a human is trying to achieve. But what it takes insight from is basically that when you're operating in modal control, so you are not, the human is not able to access all of the control space at a given time. And so when you're in operating in a certain control mode, you're operating only within a subset of the control space. That there are axes of motion that are more expressive with respect to revealing the human's intent and versus less expressive. And so an example right here is if at this the green at the bottom of the screen is the robot gripper. You can see if the red and the blue are two goals that you're trying to achieve. Translation in the X dimension is much more intent expressive, or has much more intent information in it than translation in the Y dimension. And so our idea with this work was to actually allow the robot to take a step where they put the human into the maximally disambiguating control mode. So here the human was in this study, in this paradigm, the human was able to basically push a button that says help me. It's sort of a help me help you to help you paradigm. That the robot will put you into a control mode where then if you operate in that control mode, the robot will be able to infer your intent faster and therefore provide assistance faster. So that's really the intent of this the goal of this intent disambiguation algorithm. So we ran a study where a small study with 8 uninjured subjects. There were 2 tasks. They were operating this robotic arm. They were using 2 interfaces. So they were using the head array and the joystick, and you can see what modes each direction of motion was mapped to. And what we saw was that if we look at the number of button presses, where a button pressing could either be a disambiguation request or it could be a mode switch. With the joystick, even though when we did the disambiguate, we had fewer mode switches under the disambiguation condition, but if we look at total button presses, they were actually about equivalent. So the disambiguation requests that were made kind of made up the difference. But if we're now look at using the more limited interface, we start to see a statistically significant decrease in the number of mode switches that need to happen. So I'll mention that the way that we were performing disambiguation, the way that we were reasoning over the control modes to see which would maximally disambiguate the human's intent was a heuristic process, or we were using a heuristic to do it. So in more recent work, my student Deepak framed all of this within information theory. And so what we can think about first is, let's say we're starting out with this distribution over goals. So this is we've got 3 goals. Their probability is each a color on this bar graph. And here we have a belief distribution over the goals. So for this particular distribution of goals, the entropy of that belief, the belief distribution, is high. And so what we do in this paradigm is that we actually perform what we call disambiguation nudges, where the robot will the autonomy will put the robot into a state that will maximally disambiguate the goal if the human then operates from that state. And what's important here is that the state S is actually the robot pose, or it's a control mode. So we have this augmented state space that's basically related to all the different actions a person can take with the interface, where what the actions that they can take can move the robot in position, or it can switch the control mode. And so we concatenate all of these into the action space and all of these into the state space. This disambiguation metric now is maximizing the information gain of operating from this disambiguating state going forward. And I'm not going to get into the math of that here, but I'll refer you to Deepak's wafer paper from this summer if you're interested in that, hearing about that further. So if we bring back our control sharing plot, what it looks like when all of the goals are at fairly equal probability. By definition, they must be, a third or lower, or somewhere around a third percent probability. So it would look like something like this. So we're not really providing assistance yet because we don't know where the human is trying to get to. Now, if we look at this goal distribution instead, where one of the goals has a high probability, here the entropy over the belief distribution of these goals is now low. And so here we'll provide control assistance in the same way that we have always in the past, that the autonomy has its control signal and it's going to be blended with the human's control signal. So as a first evaluation of this approach, we implemented it just within a virtual environment where we had a bunch of goals. So the goals have both position and heading. The robot was controlled with a sip and puff. So it was controlled in 1D. So you had to switch between modes, control modes, where the mode could be X, Y, or rotation. So it was a 3-dimensional control problem. In order to compute this, compute the maximally disambiguating state, We put a coarse grid around the robot and looked only at its neighbors, but that was not actually the grid, the state space of the world they were operating in. It was just to compute this Argmax optimization. And then we had a display that was telling people what control mode that they were in to help them keep track of where they were. We have several results in this paper that show statistically significant gains when you are using operating under the disambiguation condition versus only assistance with no disambiguation. But the piece of data that I wanted to show you was just looking at one example of a real-time evolution of goal probabilities. So this was actually 3 goals here. You don't see the red goal yet because it's actually, its probability has been evolving exactly in line with the blue. So it's actually hidden by the blue line. But at this vertical line here, this is where a disambiguation, where the robot was put into a disambiguation state. So I should also mention that we implemented this in a turn-taking paradigm between the human and the robot. So this was all the human's turn. We're calculating the evolution of goal probabilities based on the actions that the human's taking. And then at this time point, it becomes the robot's turn. And the robot puts the human into a disambiguating state. And so this is what it looks like now. So now all within the first couple of time steps of the human operating that state, immediately now the red goal pops up or shoots up. So it operates a little bit more. The human passes the turn back over to the robot. We have another disambiguation disambiguation moment, I guess I'll call it. And then after this, now you can see that the red pops all the way up. Everything else is all the way down to the bottom. And now it would just be only assistance from this point up onwards. Okay, so for the rest of this talk, I'm going to make somewhat of a pitch of interface awareness in assistive autonomy. And the idea behind this is that we tend within the field, or more than just tend, while we might interpret interfaces differently at the level of passing their control signal to the autonomy system, we don't reason about it individually after that point. So within my autonomy system, if I see a velocity command coming from the human, I don't do something differently with it if it derived from a sip and puff or if it derived from a joystick. And the argument that we've been, what we've been starting to see in our lab, and that's why we've been making the argument, is that this is a critical oversight. That there's a lot of information that is imprinted in these signals, and the way that we interpret them should be interface aware. So we actually started thinking about this years ago, but we weren't calling it this yet. We didn't quite, we hadn't fully realized its full scope. But what we first did for an ICAPS work back in 2016 was, and this is an old student of mine, Alex, who has long since graduated, but we induced constraints on the models within just a regular sort of A-star paradigm that we adapted, where we constrained the states and action space, and critically the state transition function based on if you were in a given state, could you actually reach what was the reachability of your state space, or did you need to press a mode switch button? Because if you needed to press a mode switch button, then that actually wasn't an action you could take immediately. So we constrained the state transition function based on the interface constraints. We also constrained the cost function, basically saying that it was more costly to reach a state where you had to perform a mode switch. So here was a state machine representation for the sip and puff. So using the sip and puff to teleoperate a simulated wheelchair. One insight that we had in this work was basically to decompose this state transition function into what are called Harrell states. And so these are basically just composite states. And we linked this also to our cost function, saying that transitions between these composite states, Q0 and Q1, were more costly than actions taken within a composite state. And then we gathered just some very preliminary data with 3 lab members using a sip and puff to operate a simulated wheelchair. And what we saw was that, and we called our algorithm constrained A-star, so C-star. And what we saw was that the agreement between the autonomy command and the human command, so this is just the human teleoperating the chair, that the human's command was more similar to the autonomy command when the autonomy was operating in awareness of these interface constraints. So why would this even matter? You'll recall that in earlier slides, we're using this piecewise linear blending paradigm. And so if you are able to choose an autonomy command that's closer to what the human was able to issue, what the human is doing, you're going to better match what they're trying to do, potentially. And so that's the whole idea behind this, is that if the autonomy is constrained similarly to the human in terms with respect to being interface aware, then when we are merging their signals together, we will have less dissonance, even though in the autonomy command will still be the safe command, if that's the reason why they're different, is to avoid an obstacle, for example. Okay, so more recently, what really kicked off this work, so we had started thinking about it years ago, as I mentioned, but what really kicked it off was a study that was done in 2018, and this was done by my student Maddie, who's been still working on this. And it started out as just a large scale usage characterization study. So we just wanted to study how people teleoperate robotic wheelchairs. So we had 7 tasks. You can see this is our lab space in the hospital. So we have these sort of simulated pieces. We have a ramp, we have a doorway, we have a curb and sidewalk. So these are all tasks that would be challenging for wheelchair operators. And so we had 7 tasks. We had 3 interfaces. So the 3 most common wheelchair interfaces: joystick, head array, and sip and puff. And then one interface was used in each session. So people came over 3 sessions. And then we started each session with a baseline, 3 baselines. One was a clinical standard, which is the wheelchair skills test that's used to assess wheelchair driving ability. And then 2 of them we developed, which were to assess interface usage. So the first was a command following task, where basically there was an arrow prompt on the screen and people were asked to reproduce the prompt with their control interface. And then the second was a trajectory following task, which was just very rudimentary visual in terms of its optics. But there was sort of a footprint of a 2D wheelchair, and you were supposed to go forwards or backwards along this path. And there's, of course, some room, there's wiggle room because the path is wider than the wheelchair. Right now, I'm going to present data from the initial use of these tasks, but I wanted to give a shout out to the iCore paper that happened just this last summer, because we now turned these 2 tasks into an app that's available for clinical use. We're going to be evaluating it with clinicians probably in this coming winter, but the idea is that this sort of assessment that's helpful for us when we're developing autonomy paradigms is also helpful for clinicians to be able to quantitatively assess people's ability to operate these interfaces. And I believe it's available for download at the Android download, the app. Okay, so some selected results from our command following task. So the first is that when we looked at task success, we did not see differences between the 3 interfaces. So we had uninjured participants and spinal cord injured participants between the 3 interfaces. We didn't see a difference in task success. We did, however, see a difference in response time, statistically significant difference. Now, we were able to dig into this a little bit more deeply with our spinal cord injured participants, because they are all wheelchair operators. So they are all experts in one of these 3 interfaces, because they use that to drive their wheelchair every day. So we took their data and we divided it into expert versus non-expert, depending on what their primary interface of use was daily. And what we saw was, again, no difference in success, but now we did see a difference in response time. And so what this is saying is that there's a difference between interfaces and response time, but however, this can be, it can improve with experience, with learning. So one of the reasons why response time can matter is that you'll remember from earlier parts of my talk that we aren't using the control signal only for control. We are blending it with autonomy signals. We're also using it for intent inference, trying to figure out which goal a person's going to. And so if there's a response time lag with one interface versus another one, or a different amount of lag with one interface versus another one, it basically means that if the human is providing a control signal, if the autonomy is taking a snapshot of the world through its sensors, coming up with an autonomy signal, and now the human is providing a control signal, but with a delay, it's now perhaps going to be aligned with a different snapshot in time for the autonomy signal. And so you can actually have these rippling effects throughout a control system because of disparities that are related to the interface in use. So we actually looked for the trajectory following. We looked at errors in intent inference. So this task doesn't have any intent as a part of it, but we actually just ran over the data, an inference engine that we use on our actual wheelchair, which is just the dead simplest one we ever use, where all we do is just forward project the current human control command a half a second into the future. So we forward project it, basically just saying, I'm not going to make any high level inference about where it is you're trying to go. I'm just guessing that if you pointed the joystick like this, in a half a second, you'd like to be right there. So we ran this over the trajectory following data, and then saw how far it was from where the wheelchair actually ended up a half a second later. And what we saw was that there were definitely differences between the interfaces. With the uninjured group, there were statistically significant differences. And what's interesting is that if we looked back at here on where we saw response time, we saw that actually the sip and puff had the longest response time. The head array was in the middle and the joystick was later. And then yet when we look at this interface, the head array is the one that had the most prediction error. And so we're not exactly sure why that's the case, but it's telling us that there's something richer going on under the surface here. So to dig into this a little bit further, Maddie tried remapping the joystick and head array to match the constraints of the sip and puff. So if we remember, the sip and puff, you'll only issue one dimensional control at a time, and it's going to be non-proportional. So it's going to be like turning a switch on and off. She just ran this on our lab members for some pilot data. But what we saw for response time, so here you see that there's a statistically significant difference between the joystick and the sip and puff. However, after we remap the joystick to match the constraints of the sip and puff, we no longer have that difference. Same thing for what percentage of time the wheelchair basically went out of bounds, that it was off the optimal path. Here we saw a statistically significant difference between both of the interfaces and the sip and puff. And then again, both of those differences went away once we had the remapping. So to take this work further and come up with it a bit more formally, we've taken a different view now on how we think we should be reasoning about interfaces and interface activation. So robot control is normally represented, this mapping between task level action and robot control command is normally something that is represented in this way. That basically, if you get a forward motion command from the joystick, then you're going to move the robot forward. You're going to move its wheels forward, something like that. And what's missing here, we're arguing that this is a user interface agnostic view of this control mapping. And that really, this is all going through an interface, and interfaces are dependent on measurements. And not only is there this measured interface command that is now mapping over to the control command. So if it's a sip and puff, for example, it's that you are blowing out and it's being detected as a hard puff, and you're saying, okay, that means I should move forward. So there's actually the physical activation of the interface, and also that there can be a mismatch between the intended activation that the human wanted to make and the measured activation. So what we did was we came up with a way, we wanted to actually model all this explicitly. So the first thing we did was we had different tasks that we would ask the person to do in order to model these stochastic deviations in user input. So these are differences between the intended and measured interface commands. So what this can look like here, so the environment that we used was a 3D environment, 3D control space for a robot, so X, Y, and heading, but using a one-dimensional interface. And this was the state chart mapping between hard puffs and hard sips and soft puffs and soft sips. So what this would mean is that, let's say you were in state X and you wanted to switch to control in control dimension Y. Sorry, you were in control dimension X, wanted to switch to control dimension Y. So you issued a hard puff, but instead it was detected as a soft puff. And so what would happen is that you would go forward an X instead of switching over to Y. The next thing we measured was, or the next thing that we would do is then we would infer the intended input. So given that we measured, or given that basically what command do we think that you would have issued if you wanted to come up with this task level action A? And so here you can see that we've got these prompts coming up that's saying, which action would it take to achieve this motion? And this is related now to the person's understanding of the robot control. And then we provided customized assistance only if there was a mismatch between the intended and measured actions. We evaluated two mechanisms of assistance. So we had a filtered mechanism where basically said, if there's a mismatch here, we're just going to block the control signal and do nothing. And then another one where we corrected it to what we thought they wanted to do. We evaluated it within this very simple virtual environment with a preliminary study with 10 uninjured subjects operating the sip and puff. And what we found was that it had the greatest efficacy when the mapping from intended to measured interface was noisy, but they had a good understanding of the robot control. So their map of what signal should be issued through the interface to realize a certain action on the robot, when that was a good model, but their ability to issue the command they wanted was noisy. That's when this paradigm had the greatest efficacy. And right now we're working on expanding this work where we're going to evaluate it on real robot hardware instead of this simplistic domain. And we're also going to relax some of the assumptions of this initial evaluation. I wanted to highlight this idea of the human's understanding of the control mapping and bring back again our list of challenges for assistive autonomy. So another challenge is the human's understanding of the machine, so of its control mappings and kinematics. If you've been watching this Jaco arm move, you know, it's got these bent links and it's not non-anthropomorphic. And so the way it moves can be unintuitive. So figuring out what kind of control signals you should be issuing in order to get motion to happen can be a challenging thing. And then that only gets all the more exasperated when you introduce autonomy, because now the command that you issued that you thought would result in this sort of motion with the robot is now being conflated by the fact that the human gave a signal like that, for example, or sorry, the autonomy gave a signal like that. And so all of these are challenges when we're developing assistive autonomy. So the last piece of work I'm going to talk about is a collaboration with Sandra Musso-Valdi, who's also faculty at Northwestern and at my hospital. And here it's that we are wanting to use a high dimensional interface based on body motions to control a high dimensional robot. So this body machine interface is something that Sandra has been developing in his group for quite some time. It's a sort of it's a suite of IMUs, a net of IMUs that are placed over the upper body. They've shown that they can map this high dimensional control signal down to a 2D control point and use it to do a variety of things. They can type on a keyboard, they can play Pong, they can do all sorts of 2D virtual tasks and also drive a wheelchair, which is a 2D task. And they've shown that people can use this interface even when they have high-level cervical spinal cord injury. So if your injury is incomplete or you might have a little bit of residual motion left in the shoulders, and that little bit of residual motion is enough to be able to operate this interface. And an advantage to using this kind of interface over, for example, a brain-machine interface is that you have to move to operate it. And so they've actually shown that in a clinical trial that you can increase lateral forces in the shoulders. And so it actually potentially can promote rehabilitation recovery. What Sandra's group hadn't done, though, is try to use this to operate a higher dimensional machine. And the question of whether or not you could, when you learn to operate the body machine interface, you learn to re-coordinate your body motions to operate this lower dimensional control point. And so even though this is a higher dimensional machine, it's still lower dimensional than this suite of sensors on the body. And there's a real question of whether or not you could actually intuitively operate in such a higher dimensional machine. Of course, we could switch over to modal control, but the whole point of this would be that we wouldn't need to anymore, that we could actually issue a 6-dimensional control signal. You know, and the sort of very obvious ways to break down shoulder motion, like doing something like this, it's sort of easy to think of how you could do it with 4 dimensions, but if you're going to do something like 6 dimensions, you'd maybe need to couple motions, or and also our patient population maybe doesn't have these clear axial movements. So it was unclear to us whether or not it's even possible to do this. But the whole idea was that we would use robotics autonomy to help with training the human, help with their understanding of learning how to operate a high dimensional assistive machine with a high dimensional interface. And so that whole idea is that the autonomy takes over part of the control signal, and that over time we step back the autonomy. So as the human's learning reaches certain benchmarks, and also in between these benchmarks that we're slowly decreasing the assistance, and then we're unlocking additional control dimensions for the human, where eventually in the end we'd like for there to be no autonomy engaged at all. And so the whole idea here is that we're actually going to use robot machine learning in order to elicit human motor learning of how to operate the assistive robot. So we have completed the first phase of this research, which was a pilot session of 10 uninjured participants over 5 sessions. This did not involve any autonomy. It was just to gather a baseline of human motor learning. We're now in the process of developing everything, or preparing to run the full study, which the full study is going to be 20 spinal cord injured participants, each coming in for 20 sessions. So it's going to be quite an ambitious study. And the results of this study are under review at the moment, but I just wanted to share 2 of them with you. So one of our somewhat surprising results. So in this first phase of the study, half of our participants operated in joint space control and half operated in end effector control, because we weren't sure which would be more intuitive. In the sense of, you're learning to remap your body motions to cover this high dimensional space. So was it going to be easier to control the position and orientation of the end effector, or to control each of these 6 joints? My guess was with the end effector, because the 6 joints of the JACO really don't seem intuitive to me at all. And what was interesting was that we saw a clear difference on day 1 in terms of which of them was more intuitive to operate. So basically no one could successfully perform. We had reaching tasks and we had ADL tasks. So this data is just for the ADL tasks. No one could successfully perform an ADL task, like throwing away this mask into the trash, on day 1 with using task-based control and effector control. And a number of people could with joint space control. But then there was almost no improvement in joint space control. So the task-based control seems to be less intuitive, but more learnable. At least this is what our initial data is showing us. And this is also what we saw with trial time, that we saw an improvement. We saw kind of similar performance in trial time. The joint space did a little bit better on day 1, but then the task space was able to improve and the joint space really wasn't. And so this is still fairly preliminary, but it's starting to give us some insights to human learning with this high dimensional interface mapped to a high dimensional robot control. Okay, so I just wanted to tack onto this list co-adaptation. So of course, if you are changing the autonomy over time, because you're trying to adapt the human, then of course now the human needs to learn something new. And so this co-evolution of autonomy and human learning is a challenge as well for assistive autonomy. Okay, so that's about it for this list. I thought I'm just going to close with a couple of thoughts about adaptation under assistive autonomy. I gave one of the plenary talks at ICML a couple of years ago, and the space in which I work is not a space that they typically are exposed to. So they were interested to know my thoughts about machine learning within that space, and I focused on adaptation under assistive autonomy. So, what are some of the considerations that we need to think of? The first big one I'd say is, what kind of feedback signal are you going to use for learning? So is it a reward? Is it a supervised label, a correction, a demonstration? Is it explicit, the human saying do this? Is it implicit, you're saying, I don't think the human liked that because I could observe that they did this other thing? So what kind of feedback signal are you going to use? Of course, this masked and filtered of information, that this is really a challenge. So, if you saw the human do something, does it mean that you should pay attention to it and learn from it, or was it aberrant? Did they not mean to do it? And so you shouldn't learn from it. In fact, you should try to correct it with your autonomy. There's a lot of temporal considerations. So people's physiology is changing. They might be regaining ability because they're in rehabilitation. They might be losing ability to a degenerative disease. Their physiology is changing a lot. Their familiarization with the technology that you present to them is changing. And so the question of what the rate of adaptation should look like based on the fact that all of these other things are changing is a research question unto itself, I'd say. And then of course the human autonomy co-adaptation, which is just going to make everything a lot harder. Okay, and that's it. So the title of my talk was Assistive Autonomy Revisited. The reason why I used the word revisited was really largely because of this whole idea of interface awareness and assistive autonomy. And I'll mention, actually, just last month we were awarded a grant. Thank you, NSF. We were awarded a grant to look entirely at this topic. So there should be more coming out on this from my lab in the coming years. And then also the whole idea of intent disambiguation. Instead of different ways to perform inference, how can you actively gather information that will help you perform better inference, regardless of what kind of inference engine you're actually using. And so that's it. I'd like to thank my current lab members on the right and my the graduated lab members, or I shouldn't just say graduated, one was a postdoc, but the prior lab members whose work was featured in this talk on the right, and then my funding institutions and affiliations. And I'm happy to take some questions.
Thank you, Dr. Argall, excuse me, for that excellent talk. So I can help moderate for the questions. I'll keep an eye on the chat. In the meantime, I had just 1 or 2 questions to get us started. So you mentioned a variety of different existing interfaces. Do you think that we should also be considering making new interfaces, or do you think the ones we have are good? We just need to figure out how to work with them.
No, I think that we certainly should be making new interfaces. I mean, these interfaces leave a lot to be a lot to be desired. The reason to be working with the interfaces that are out there, and specifically my lab, with the exception of the last piece of work I showed, my lab exclusively uses the commercially available interfaces that are used to operate wheelchairs. And the reason why we do that is because they are broadly user vetted, they are broadly deployed, they're covered by insurance. And so as we think about people adopting our intelligence technology, this is just one less thing that they would have to adopt that's new. The idea is also that, if you had better interfaces and better quality data coming through those interfaces, you would only do a better job. So if we can do a good job with these more challenging interfaces, then, we'll only do better if we have better information. But and so that's why we've chosen to focus on that in my lab, but certainly new interfaces is also a research thrust that should be happening in parallel. Yeah.
Great. So one question that was messaged to me, perhaps by mistake, was, so when you're making these devices, the question is like, what are the challenges for actual implementation in the world? Like we see them occasionally, but what would it take to see them more often? Is it just like there are not enough people who need them? I don't think so. And what do you see as some of the practical challenges to seeing more of these autonomous wheelchairs or autonomous assistive devices in our everyday lives?
So are you asking them about the challenges to getting it running in the lab, or are you talking about the challenges to deploying it out in the real world?
I believe the question is about deploying it in the real world.
Yeah. So there's a number. Yeah, there's a number of challenges. So I guess I'll start out by saying that there is one company that provides a sensor-based safety package for wheelchairs. They came on the market in 2022. They're actually collaborators of ours. They're awesome. And they provide only subtractive assistance. So they only ever take energy out of the human's control signal. They don't never add to it. So they can do it, directionally. So they can steer you because they slow you down in one direction. And they do this to avoid collisions and avoid drop-offs. And the reason why they don't add to the control signal is because then they would no longer be FDA Class 1 exempt. And so I think once we start talking about autonomy being pulled into the control loop, into a commercial product, we have to start thinking about regulations. How do you actually ensure safety? Of course, the machines themselves are already FDA approved, they're already human safe. And so it's not that we need to start from ground zero and ensure the safety of the entire machine. If you're running the control signals through the proprietary control loop, then all that's fine. The question is, if you have the autonomy issuing a control signal, especially if it's now for people who otherwise couldn't be issued wheelchairs because they can't issue the control signals safely or reliably themselves, then now we need to have some sort of guarantees on that. And I have never worked in regulation. I do know that the FDA has been looking at autonomy right in their regulated devices for a while now, and that I think I talked to them probably more than 5 years ago. And at the time they thought it would be 10 years out. So maybe we'll start hearing something from them in the next couple of years. But I'd say that that's certainly going to be one big barrier. And then of course it always is about user adoption, and that it needs to be cost effective. Lucy, for example, they've had a lot of success with people getting it insured or reimbursed through insurance, but they don't have their own code, which the coding makes all the difference in the medical world. If you have a code that you can say it is this kind of device, then there is a whole formula that says you get this amount of reimbursement for it. If you don't have a code, every time you want to get reimbursed for that device, you have to justify why it needs to be this price, why a person needs it in this way. And so it's just much, much, much harder. So until we have codes dedicated to these things on insurance forms, then it's going to be that it's a lot more overhead to get reimbursed, and it's not going to be as accessible to every person.
Okay, that's a really a lot to think about there. One final question. I know we're almost out of time. One final question it's on the chat. Could you please explain about the action mapping between the wearable device and the robot arm in the last project? I believe they're talking about the multidimensional wearable. Yes.
Sorry, but explain the what between them?
How do they map between the two?
Oh, okay.
Yeah,
so it's using a dimensionality reduction algorithm. Sandra's group traditionally had always used PCA, which, in some ways, perhaps sounds like it's an antiquated machine learning paradigm, but I think it's actually a really elegant solution for this problem because it's extracting the axes of maximal variance, which means that that's actually the axes of maximal movement for the person with limited mobility, because they would have them do this sort of, they called it their calibration dance. So they would move as much as they could, just open-ended. And then from that data set of movement, they would extract these axes of maximal movement. Now, that works quite well when you want to actually find these two principal components of movement. If you now want to look at like 6, like PCA isn't the best option anymore because actually PCA is designed to capture as much variance as you can within the first two components. And if you actually want 6 components, you don't want your variance to like drop off that quickly. So there's a lot of tricks that we did to try to like have it decline more steadily. And we're also currently we're currently looking at autoencoders, like as one does. But yeah, that's in that actual paper. It was like a jimmied up version of PCA, I'd say.